we're going to talk a little bit about using algebraic analysis to study objects in motion. Now, objects that are moving at a constant velocity, good old v equals delta x over t, will do most anything you need to find out about the motion of that object. But when objects are accelerating, it becomes a little more complex. And there are four important equations to study the motion of objects that are accelerating uniformly, which means constant acceleration. Acceleration is not varying. Now, instead of just giving you these four and just saying, here, memorize them, they're magic, what we're going to do is briefly run through a little derivation of each of them, because you really shouldn't accept anything from a teacher just because he says, hey, this is right, take it. I want you to understand why they work. So let's start off with a brief talk about what average kind of means. You know that when you average two numbers together, you add them up and divide by 2. Well, for an object that's accelerating, you can take its initial velocity, final velocity, add them up, divide by 2. That would give you an average velocity. Now, we've already said that average velocity is also delta x over delta t, and we could rearrange that to solve for delta x, which would be average velocity times t. So if we combine those two equations, we get the first of our four important kinematics formulas, which is delta x equals initial velocity plus final velocity over 2 times time. In order to come up with the second of our equations that we want to learn about, let's look back at what we found out about acceleration when we were studying motion graphically. We know that the slope of a velocity time graph is change in y over change in x, and we know that velocity is plotted on the y-axis, time on the x-axis. So y2 minus y1 over x2 minus x1 can literally be interpreted as final velocity minus initial velocity divided by final time minus initial time. Now, when we're talking about just measuring things that move and timing them, we normally don't look at clocks and really have an initial time and final time. Most of the time we stop a stopwatch, and so we just have a time. Our initial time usually is 0. So we end up with an equation that looks more like that. If we rearrange it, we get number 2 in our list of equations for uniformly accelerated motion. Final velocity equals initial velocity plus acceleration times time. Looking at that formula we talked about for average velocity, the idea that initial plus final over 2 gives you an average. If we look at that and we take into account our latest formula we derived, which gives us a new definition for final velocity, we can substitute that v sub I plus at in for final velocity in the average velocity formula. And we get a new, if you look at the end, a new expression, which is v sub I plus 1/2 at. Now you'll remember that we rearranged the old average velocity formula and got delta x equals average velocity times t. If we stick our new expression for average velocity in this equation, and then if we clean it up a bit, we get the third kinematics equation for uniformly accelerated motion. Delta x equals v sub I t plus 1/2 at squared. Finally, let's look at that equation we just derived, and then let's also look back at what we said was acceleration. Final velocity minus initial velocity over t. We can rearrange that expression and solve for t. If we do that, we can substitute it into that top equation in place of t. Now you see it looks quite messy, but if we clean it up a bit, we get v sub f squared equals v sub I squared plus 2ax. It's quite useful when you don't know time. Well, there you go. We've got the four equations for uniformly accelerated motion. If you look at each of these equations, you will see that they each offer something a little different. The top equation, if you know distance, initial and final velocity and time, but you don't know acceleration, that's the equation you need to use. If you know initial and final velocity, acceleration, and time, but you don't have any distance information, that second equation will work for you. If you're interested in dealing with distance, initial, velocity, time, and acceleration, but you don't have any final velocity information, the third equation will do it. And if you're dealing with initial and final velocity, acceleration, and distance, and you don't know anything about time, the last equation will do it for you. Now, one thing worth pointing out is quite often when we deal with objects that accelerate, they accelerate from rest. The most common example is probably anything that's dropped. When you hold something to drop it, its initial velocity is 0. Then when you release it, it accelerates. Or if an object is at a stop sign or a red light, when it takes off, its initial velocity is 0. And notice in these equations that when you fill in 0 for initial velocity, they become quite simple, really easy to work with. So that's quite often our favorite case, initial velocity 0, because it makes the math so easy. But those are the 4 equations that you need to be able to use well to solve problems for uniformly accelerated motion.